Hi, this video is about looking at light kind of as photons, as made out of particles. And it really is module 4, the second part of lesson 1. And in our book, it's page 111 to 115. So light, we've been talking about light, and we have different colors and different frequencies of visible light. And now there's been some experiments and some things where we can't really explain it unless we think of light not as a wave, but as made out of particles, which we call photons. So let me explain that. So light is a wave and it is a particle. It just depends on what you're trying to explain. So it has a dual nature. So the first thing in this one is really simple, but if you heat something like a piece of metal, it kind of glows red, and it doesn't glow other colors. You don't see it glowing purple or green or blue, at least not in this picture. So this is something that really couldn't be explained, because if it were that energy could be emitted at every level of energy as a wave, then we would expect all the colors, but we only see certain ones, because really what's happening is it's emitting particles of electromagnetic radiation, which I know is weird, and so I'm going to keep talking to you about it. So this is what we call the quantum concept. So matter, including atoms, that's what we're mostly interested in, can gain or lose energy in these little pieces called quanta. Quantum is just that minimum amount of energy then that can be gained or lost by an atom. So, and then, just a little analogy is, if you're, walking up a ramp, you could stop anywhere. So this is not quantized. This is continuous. Energy is quantized, kind of like a ladder. So like for example, an electron could be here and it might absorb energy and move to here. It can't be kind of in between steps. That's what it means to be quantized. So a quantum is a piece of energy that can be gained or lost, and it's not continuous. It's like a piece. So I have a couple analogies for you in just a second. We can actually calculate the energy of a quantum, and that would be equal to h nu. So E is for energy, and that's going to be in the unit joule, and we use the capital letter J. H is Planck's constant, and you don't need to memorize it. It's on your pink sheet, but it's equal to 6.626 times 10 to the negative 34th joules second. And then this is still nu, Nu, the Greek letter, which is for frequency. And so that's going to be in inverse seconds or hertz. And we're going to use the equation in just a second. But this is, so really those quantum, the energy of that quantum, it's kind of like bricks or Legos. You know how you would, if you were playing with Legos, you could add, 6 Legos on top of each other, take away 2, but you're always dealing with full Legos. Similar to my little brick analogy, you can't really add, a 0.3 of a brick. So similarly, atoms will gain or lose not bricks, but energy in these, this energy, this quanta of energy. So there's something called the photoelectric effect. This was another thing that, was unable to be explained when we thought of light as just a wave. So what it is if you have a metal and you shine light on it, and let's shine some, so when we know our colors of the light, by the way, red light has the least amount of energy. It's going to have the lowest frequency, whereas the violet will have the most energy and the highest frequency. So if I shine red light on the metal, nothing happens, even if I make it more intense. So I can kind of change it into, more of the oranges, still nothing. So if we thought of light as just a wave, it would be like eventually, if I shine my light on it long enough, it should eject electrons. That's what's going to happen. But that doesn't happen. It only happens at kind of a threshold frequency or wavelength. So green light has more energy. And then I keep going. And eventually, there we go. So eventually I get to a high enough frequency color that carries quantum of energy that is enough to kind of dislodge some of those electrons from the metal. So the photoelectric effect really was just a thing that no one could really explain, and until we thought of light as being made up of photons. So the metal has to be hit by a photon that has enough energy. The energy equals H times nu. It has to be enough energy, and if it doesn't, it won't work. So that is what the photoelectric effect is. So let me find my iPad again. Uh-oh. Okay, I think I got disconnected. Sorry, I'm going to reconnect. And sorry for the delay. And here we go. So just explaining the photoelectric effect. So this is another, phenomenon that we weren't able to explain it until we started to think of light as being made up of particles. So this is a good picture, I think, to explain the photoelectric effect. In fact, in class, I had people draw like a red photon of energy. So remember, it's going to have energy equal to really directly proportional to the frequency. So a red is going to have a low frequency, large wavelength. And then if I were going to draw, like, let's say a blue photon, I'm going to show it bigger. I'm going to show a higher frequency, and I'm going to show that it has more energy. So if my blue photon hits the metal, then it's possible that that's enough, and it was in the one I just showed you, to kind of hit some of the electrons off of the metal. If my red photon goes there, it's not enough energy. So the atom has to absorb a certain amount of energy or quantum of energy in order to exhibit the photoelectric effect. Here's another picture. So like these would be your blue photons, and the electrons will, start to move off of the metal. Red, nothing happens. Not enough energy. So Einstein, of course, was the person that kind of was able to explain this. And he was the first to propose that light has that dual nature. It is a wave and it is made up of particles. So the equation that we just covered for the quantum, we can also say is the energy of a photon. And a photon is a piece of electromagnetic radiation. It's when we're thinking about color or any one of the different types of electromagnetic radiation, when we're thinking of it as made up of particles. Here we go, finally, the photon definition. So it's really a piece or particle of matter, and it carries a quantum of energy. So we were drawing our photons. I like to draw them, so we know it's carrying a certain amount of energy equal to Planck's constant times the frequency. And then if we have like a violet photon, it's going to have even more energy because the frequency is higher. This little picture, here's your photon, there's your quantum of energy. So let's do a calculation. The calculations are fairly simple. So in this question, we're looking at calculating the energy of the photon of the violet portion of sun's light. So we know the frequency is 7.23 times 10 to the 14th inverse seconds or hertz. We know Planck, and we're looking for energy. So energy equals Planck's constant times the frequency. So it's really pretty simple. We're just going to plug those two numbers into our calculator and calculate. I'm going to write my inverse second this way. And the reason why I'm doing that is so that I can show that my seconds cancel and I end up with joule, which makes sense because I'm solving for energy. So when I do this, I'm just plugging in my calculator. If you're using your EE button, you're putting 6.62 EE negative 34 times 7.23 EE 14. And when I do that, I get 4.79 10 to the negative 19th joules. That's the energy, the quantum of energy that is carried by that particular frequency of photon. So next thing we're going to talk about, and this is the lab that we did today, where we'd done this in a POGL on paper, but now we got to see it. So we have our hydrogen gas and we put it into a lamp with electricity. And then we looked in our, we used a spectroscope, which spread out the colors. And we were able to see these different bright line spectra for hydrogen. So why do we only see certain colors? If we look at white light, we get what we call a continuous spectrum where nothing's missing. They're all there. They're just kind of blurred together. Emission spectrum are like fingerprints because each element will have its own distinct set of lines, of bright lines. And what's happening and why this is also proof that the energy of an atom, the energy levels of an atom are quantized. So the electrons have to go from one level to another in steps, like they can't be in between levels. So on your lab, well, one thing I would do is grab your POGL and go to the page where you have the 4 circles. But let's, on the lab, I'm going to show you one. So I would label the energy levels just like they were on the POGL. And then I would add a 6 in case, I'll show you why. And what I'm going to show you is kind of what's going on to give us those bright lines. So if I have my red photon, remember the wavelength is, the frequency is pretty low. And I'm going to have an electron sitting at n equals 2. And it's at low energy. It's attracted to the positive nucleus, just doing its thing. But once I let that electron absorb that red photon, it will jump to n equals 3. And I'm going to put a kind of dotted line around it because it's just going to be there for a second. So the electron has to, and we're going to call this absorption. So it absorbs the photon of energy, and then it wants to return back to where it was. And when it returns, we call that emission. And when it undergoes emission, it gives back that energy of the photon as a color. So it's going to give me the red color. Sometimes the transitions are in ranges where we wouldn't be able to see them. Like, for example, if we went from like n equals 8 to n equals 2, it would be a wave that is in the ultraviolet and we wouldn't be able to see it. So what I want you to do is pick another color from your POGL. So you're going to either do violet, I can't remember the names, blue violet and blue green maybe. Pick one of those and show the photon. So you're definitely going to want to draw a photon that has more energy, higher frequency, and draw another electron and show that the photon is absorbed and show the absorption and the emission and the color that it's going to produce. So the color is going to have a higher frequency